Okay, hello everyone. So today we are going to start reaction mechanism. In reaction mechanism, we have reactant species. It is treated with reagent in presence of solvent. In presence of solvent, and then it forms product. Again, listen me. In a reaction, we have reactant molecule, reagent, and solvent. It is not necessary reagent always be top of the arrow. Sometimes it can be in the left, like here, reagent, reactant here, solvent, and product. In any chemical reaction, it is an interaction of reactant and reagent. My request to everyone, please turn off your mic and camera. So I said that it is an interaction of reagent and reactant in presence of solvent. Sometimes solvent can be present, sometimes solvent can be absent. It is not necessary in every chemical reaction we have a solvent, but most of the reaction have solvent. Okay. So first I am going to categorize the solvent. Clear? Let's talk about the category of solvent. Solvent is of two types, polar and non-polar. Please turn off your mic, everyone. Now polar is divided into two categories. Polar protic, polar aprotic. In reaction mechanism, polar solvent is more important, especially the category of polar protic and polar aprotic. Non-polar is not important, okay? So we can categorize the polarity and non-polarity on the behalf of dipole moment. There is a term called dipole moment. Dipole moment. So let me tell you what is dipole moment. It is a vector quantity. Vector quantity. Vector quantity always have direction. Means suppose you have AB bond and I am saying electronegativity of A greater to B. So arrow towards A like this. Clear? If I am saying B is more electronegative to A, then the arrow towards B. Clear? So they have dipole moment. We can say they don't have dipole moment zero. They have some dipole because they have polarity. This is more electronegative, so delta negative. This is less delta positive. This one is more negative, delta negative, and this one is more less. This is delta positive. What is zero dipole moment? For example, I am saying suppose we have A, B, and here B. If you are going to check the suppose I am saying electronegativity of B greater to A. It means this is negative here, this one is negative here. So A to B arrow should be like this and A to B arrow should be like this. So now you can see the net dipole is here 0 because the force is equal and opposite. Make sense? Please tell me everyone. Perfect. For example, suppose we have a molecule called CCl4. CCl4. And we know that chlorine electronegativity is greater than carbon. So top chlorine would be this, right hand would be this, left and downside like this. So you can see here, this and this is equal and opposite, so it would cancel out each other. Similarly, right and left will cancel out. So net dipole is here 0. So whenever your dipole moment is 0 for any solvent, that could be considered as non-polar. Example CCl4. Okay. So CCl4 is a non-polar solvent. Example CS2 molecule. Example CO2 molecule. You can see CO2 structure is like this. And oxygen electronegativity is greater than carbon. So it would towards oxygen and here towards oxygen. So equal and opposite. So mu is equal to 0. That means net dipole 0. So this is a non-polar solvent. Same you can do with CS2. Look at here. 0. What is polar? Polar means net dipole does not equal to 0. Clear? Like there is a difference in electronegativity here as well. For example, like H2O. Here we have lone pairs. So this hydrogen oxygen arrow towards here, this hydrogen oxygen towards 0, like this. So net dipole is not 0 here. Clear? So what is polar protic? Protic means proton. So whenever hydrogen is directly bonded with fluorine, oxygen and nitrogen, that can be considered as polar protic. For example, H2O, ammonia, alcohol. Can you see this? It makes sense. They are all polar protic. Why? Because there is a linkage of hydrogen with oxygen, hydrogen with nitrogen, hydrogen with oxygen. Makes sense? Please tell me everyone. If I am going to ask anything to you, please say everyone. Next, polar aprotic. Yeah, you can say like hydrogen bond. Yes. What is polar aprotic? Polar aprotic means hydrogen should not be bonded with fluorine, oxygen and nitrogen. For example, look at CH3CO, CH3. You can see this is polar, but hydrogen is not associated with any of the electronegative element like fluorine, oxygen, and nitrogen. So this is polar aprotic. Look at this one. Hydrogen is not bonded with them. So this is also polar aprotic. Make sense? Please tell me everyone. Okay. Now I'm going to give you some solvent and you have to categorize the nature of that particular solvent as a polar protic and polar aprotic. For example, this is the first one. Okay. We can leave the last one. Okay, last one is also you can consider. Look at the very first one. What is the first one? PP or PA? Yes, hydrogen is not linked with fluorine, oxygen, and nitrogen. You can check the structure. So this is polar aprotic. Okay. What about the second one? And this is very important solvent, the first one. You should know the name of this solvent as well. In short, this is called DMF. Very, very important. Because in exam, you don't have a structure of DMF. So this is called dimethyl. Dimethyl. This is dimethyl. And this part is known as formamide. So this is dimethyl formamide. Okay. What about the second one? Polar aprotic or protic? I think you already told me this is polar aprotic. Yes. What is the name of this? This is dimethyl acetamide, DMA. Dimethyl acetamide. What about third one? Polar protic or aprotic? I am again telling you, whenever hydrogen is not bonded with fluorine, oxygen, and nitrogen, it would be polar aprotic. Yes, polar aprotic. This is called acetonitrile. Acetonitrile. And what about this fourth one? Yes, polar aprotic. This is again very important. DMSO. This is called dimethyl sulfoxide. Dimethyl sulfoxide. At this moment, this DMF, DMA, DMSO, very, very important. What about this fifth one? This is called THF, tetrahydrofurane. Tetrahydrofurane. Polar aprotic, yes. Why? Because this carbon have two hydrogen. This carbon have two hydrogen. And you can see hydrogen is not bonded with oxygen, fluorine, and nitrogen. It is bonded to the carbon. So this is polar aprotic. Okay, what about this? This is called crown ether. This is known as crown ether. This is again polar aprotic. Very good. What about H2O? Seventh one. Yes, this is PP, polar protic. What about this carboxylic one? Polar protic. Good job. What about the ninth one? Last one. First of all, I would like to tell you this is non-polar. This is non-polar. Because there is no polarity. If you have any hydrocarbon, it's generally non-polar. Hydrocarbon is a non-polar. So whenever you have a non-polar structure, that would be considered as non-polar solvent. Non-polar solvent. Okay? It makes sense, everyone? Please tell me. Solvent. Any doubt in the solvent case? Perfect. And one more thing I would like to tell you. If you are going to cover substitution reaction and elimination reaction, then you should know especially these solvents like DMSO, DMF, acetone, and polar protic is very simple one, like whenever hydrogen is bonded with fluorine, oxygen, and nitrogen in any structure. Generally H2O and ammonia is the most common one. Okay. So these three in the polar aprotic, and in polar protic, this one is very important. So you should know this one at least. Clear? Now next is, I am going to categorize this reagent, the attacking species. So reagent, I already told you, reactant interacts with the reagent in presence of solvent and that forms product. We have done the effect of solvent, like we have done the category of solvent, basically type of solvent. Now we are going to move into reagent. Reagent is of two types. Electrophile and a nucleophile. Electrophile we can represent as E plus in short, and nucleophile is Nu minus. Clear? So let me introduce first the electrophile. Look at the wording here. Electro means electron, phile means loving. So we can say electron loving species, electron loving species. The second, it is electron deficient as well. It is electron deficient species. And the next, electron loving, electron deficient, and we know that electron deficients are Lewis acid. So it acts as Lewis acid. Okay. So how we can recognize any species as electrophile? So we can say here the very first case. In general, positive charge containing species acts as electrophile. Positive, like here H plus, NO2 plus, Br plus, any carbon containing carbocation, Cl plus, any species, most of the time they can act as a electrophile if this has, if that one have positive charge like I plus. Okay. So generally positive charge is considered as electrophile. But there is a condition, incomplete octet. Incomplete octet. Do you know what is octet? Please tell me, everyone. Do you have any idea about the octet rule? Octet means 8 electron rule. Let me tell you how to calculate the 8 electron system. Whenever you have a single bond, that means 2 electron. Whenever double bond, that means 4 electron. Triple bond, 6 electron. It means every single bond can give you 2 electron. Similarly, lone pair can give you 2 electron. Negative charge can give you 2 electron. But positive charge have 0 electron. For example, suppose we are going to calculate the octet over this carbocation, this one. Octet always calculate the central atom. Do not apply octet over hydrogen because for hydrogen it should be duplet. Okay. So if you look at this carbon, how many electron around the carbon? You can see we have 3 single bond. So 3 single bond means 6 electron. Do not consider positive charge because positive have 0 electron. So 6 electron, which means less than 8 electron. So less than it means it is incomplete octet. So incomplete means it is acting as a electrophile. Make sense? For example, what about this species, NH4 plus? You can see this one has a positive charge, but it is not electrophile. Why? Take your time and let me know. This ammonium ion have positive charge, but it is not electrophile. The reason is that it has a complete octet. You can calculate here single, 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 and single, 4 single bond, which means 8 electron around nitrogen, which means complete octet. That's why it is not electrophile. Same with H3O plus. You can see there is a one lone pair as well here. So 2 to 4 to 6 to 8, 8 electron. So this one is not electrophile. Make sense? So positive charge is not the necessary condition for electrophilicity. In general, most of the carbocation, most of the positive charge containing species are electrophile, but they have incomplete octet. Okay. The second condition, if you have what is neutral electrophile? Neutral electrophile. Here we can say vacant p and vacant d orbital. Vacant p and vacant d orbital containing species are electrophile. Example, AlCl3, aluminium have a vacant orbital. FeBr3, AlF3, BF3, BH3, boron also have a vacant orbital. BCl3, So they have vacant orbital. Let me tell you a simple example of boron, why you can say they have vacant orbital. So boron atomic number is 5. If you are going to write down the configuration, it would be 1s2, 2s2, 2p1. So yes have 2 electron, p have 3 blocks and just 1 electron. This is ground state configuration. So in excited state, you know that one of the s orbital can jump in the p. So you can see still they have vacant space. So this is P. So we can say this one have vacant P. So all the species which has vacant P and D can act as electrophile. Make sense? So that's why boron containing species are acting as a electrophile. Clear? So you can just memorize the first element like aluminium, iron, boron. Okay? And these are the most common example. Any doubt? Perfect. The third case, polar groups. Suppose we have AB bond and I am saying electronegativity of A greater to B. So A will hold delta negative, B would be delta positive. So this delta positive means there is a partial deficiency of electrons. So this one acts as an electrophile. For example, C double bond O. So you can see this is more electronegative, this is less. So this carbon would act as an electrophile. Like CO2. Carbon have a partial positive, so acting as an electrophile. Like acyl halide, if you look at this group, carbon is again, electron deficient because of delta positive, so acting as electrophile. It makes sense. Look at this sulfur. This sulfur have polarity delta plus, delta minus, so sulfur can act as electrophile. Any doubt? So at this moment, we have covered three kind of electrophile. The first, positive charge containing. Listen me, we are not talking about symmetric here. There is no mean of symmetric or asymmetric in CO2 molecule. We have to just look at the polarity. Whenever there is a difference in electronegativity, that means this carbon is electron deficient and that can act as an electrophile. Clear? Okay. So we have three category. First, positive charge. Second, neutral one. And the last you can compare as polar one. You can say polar one. So these three we have electrophiles. Now the next is nucleophile. So nucleo means nucleus, phile means loving, so we can say nucleus loving. Okay. So the very first here, it is electron rich species. Second, nucleus loving. If any system is electron rich, it means it can act as a Lewis base. Do you know what is Lewis base? Please tell me, anyone. What is Lewis base? Yes, electron pair donor. Yes, electron pair donor. So electron rich, nucleus loving act as a Lewis base. Now what is the condition for a nucleophile? So very first we can say in general, negative charge and lone pair containing species acts as nucleophile. So if any species which have lone pair or negative charge, for example, H2O, ammonia, alcohol, amine, Cl minus, Br minus, iodine minus, H minus, any carbon which have a negative. So they can act as a nucleophile. Make sense? SH minus, OH minus, they are all considered as a nucleophile because they have the lone pair as well as negative charge. You can also, categorize the nucleophile in two parts. The one is charged one, second one is a neutral one. Charge and neutral. So neutral is your lone pair one, lone pair, and charge is your negative charge. Make sense? But both are nucleophile. Clear? So this is a neutral, this is neutral, this is neutral, neutral, and this is charge one, charge one, charge, charge. Make sense? Carbon double bond carbon, carbon triple bond carbon, and benzene can act as a nucleophile. Acts as nucleophile. It needs to have a lone pair and negative charge both right to be a nucleophile. Anyone, either negative charge or lone pair. If it has both, then that's fine. This can be considered as a nucleophile. Okay. So I said that double bond, triple bond, and ring also can act as a nucleophile. Make sense? Perfect. Now there is a term called nucleophilicity. Nucleophilicity. Nucleophilicity is like strength of nucleophile. This is strength of nucleophile. And this is very, very important topic in DAT. A question can be asked, you have some nucleophiles and you have to arrange them in the decreasing order of their nucleophilicity. So nucleophilicity is strength of nucleophile, which can also be considered as tendency to donate electrons. Clear? Make sense? Very good. So the very first here effect which can affect the nucleophilicity, which is electronegativity. Electronegativity. Can anyone tell me what is the trend of electronegativity in the periodic table if you are moving left to right like this? If I am going to move left to right, what is the trend of electronegativity? Yes, on moving left to right, electronegativity increases. Okay, very good. Could you please tell me what is the definition of electronegativity? Means what is the concept of electronegativity? What is basically electronegativity is? Anyone can tell me? Okay. Electronegativity is, no, it is not an energy to remove electron. Oh, hold, yes, it is a tendency to grab electron basically. Electronegativity is a tendency to grab bonded pair of electron. Suppose I said AB bond and I am saying electronegativity of B greater to A. So B will hold the bonded pair of electron like this. If A is more electronegative, then we can say A can hold. Yeah, that's right. Makes sense? The electronegativity concept means tendency to grab the bonded pair of electron. And what is a nucleophilicity? It is a tendency to grab electron. Tendency to grab electron. And nucleophilicity, tendency to donate electron. That's why electronegativity and nucleophilicity have opposite relationship. So more electronegative element can behave as a poor nucleophile because it do not want to donate its electron. They don't want to donate. Make sense? So if electronegativity increases, nucleophilicity decreases across period. Please tell me it makes sense. My request to everyone. Okay, now the next size, second. You can always consider size in same group element, same group. This movement is called group movement, left to right is called period movement. Okay, this is group. So if you are moving top to bottom, size increases and nucleophilicity also increases. Okay. So whenever you are moving top to bottom, like we are moving fluorine to iodine, iodine has the biggest size. So iodine tendency to donate its lone pair of electron is very easy. The reason is that if you have a small size and you have a negative charge, then this negative is very close to the nucleus, so they have a very strong attraction. But if suppose we have a big size and then negative, and it is far from the nucleus, so the attraction force is very less. So this is weakly held with the nucleus. So this bond is very weak. This interaction is very weak. So we can break this bond very easily, the attraction. So we can remove the electron very easily. So bigger size can be a good nucleophile. Make sense? So iodine minus is better than Br, then Cl, then F. Clear? So whenever you have a comparison in the group, always look at the size, and whenever you have in period, look at the electronegativity. Any doubt about it? Okay. Now the third factor is resonance. Yes, fluorine is a nucleophile, yes, because of lone pair. Now look at these two species and tell me which one is in the resonance, one or two. I have discussed a lot, resonance in my previous videos. So you can see this negative and the double bond is in the alternate position. So it is in resonance. And if you want to draw its resonating structure, so you know that it would donate the electron like this. But here my negative and lone pair is not in resonance. So it can donate its lone pair of electron to any species. So this electron is free for the donation, free. But this is conjugated. It is busy in resonance. So if it is busy in resonance, it means it is not available for donation. Make sense? So that's why it is a poor nucleophile and this one is a good nucleophile. Make sense? So non-conjugated lone pair is good nucleophile. Clear? I have a question for you. We have two lone pair here, 1 and 2. Let me know which one is a good nucleophile. I told you non-conjugated lone pair is a good nucleophile. Organic chemistry is all about revision because all the topics are related to each other. Whenever you are going to move in the next chapter, the previous would definitely help you. This lone pair is busy in resonance. You can see this lone pair and double bond in alternate. So this is conjugated. And this lone pair have a double bond as well, means this nitrogen have a lone pair and double bond both. So double bond is here conjugated, lone pair is non-conjugated. I have discussed this topic in my previous videos. Please watch that one. Please, revise everything before the next session. So this lone pair is a non-conjugated. It means it can donate its electron very easily. So this one is a good nucleophile. Make sense? The next is steric hindrance. If you look at this steric crowding here, 1 and 2, this one is a bulky one. Basically, nucleophilicity is a tendency to donate electron, which means it is a kinetic property. So whenever anything is kinetic, the size is very important. For example, this is a bulky one, okay? This is a bulky one. So the movement of this group is very complex, but this is a lighter one, so it can move very easily. That's why it is a good nucleophile. Clear? And you can apply this concept whenever donor atom is same. You can see both here oxygen. That's why I'm saying steric crowding. And then I say that small size have better nucleophilicity. Do not apply this concept in group because there is a different atom. Okay? Chlorine, chlorine, bromine and iodine. So do not apply the bigger size would be a lower nucleophile. No. We can't apply this concept in the same group element. Whenever donor atom is same, and there is a steric crowding, then you can say this line. Clear? Make sense? Okay, I have some question for you. Yes, of course. The same one you're talking about, the steric crowding one. Okay, suppose you have CH3NH2. Suppose you have CH3NHCH3. Or basically, wait. Now look at this. This one is same donor atom. This one have bigger size. So this one is a good nucleophile. Clear? Okay, now I have some questions for you. Arrange them in the decreasing order of nucleophilicity. The first one, and one more thing, if you have a same donor atom, note point, same donor atom, then negative charge is better nucleophile than lone pair. Okay, like here, they have oxygen. So this is negative, this is lone pair. So this one is a good nucleophile. Suppose we have NH2 minus and an ammonia, then NH2 minus is a good nucleophile. Suppose you have RO minus and ROH, then RO minus would be a good nucleophile. Make sense? Okay. Try them, the very first one. What is the correct order of nucleophilicity? My first question, is this related to the electronegativity or size? Electronegativity means period, size means group. Look at the periodic table first of all. Elements in the periodic table are arranged like that: B, C, N, O, F. So you can see C, C, N, N, O, O, F, F. So this is related to the period. So if you moving left to right, electronegativity increases, nucleophilicity decreases. So less electronegative would be the better nucleophile. So it is arranged in a proper way. So it should be the correct order. Make sense? Please tell me everyone, it makes sense. What about the second one? This is in group. In group means size. So bigger the size, stronger the nucleophile. So it should be like this. Clear? We have done this already. What about this? Yes, oxygen and sulfur belongs to same group. So sulfur have bigger size. Make sense? What about this? Nitrogen and phosphorus belongs to same group. Phosphorus is below to the nitrogen. So bigger size of phosphorus. Make sense? What about here? You can see here the donor atom is oxygen. So it is not the rule of electronegativity and size. Now apply resonance and all. No. Wait. This is not the steric effect because the groups are not same. This is benzene, this is carbon acyl. Steric means all the related groups are like alkyl one. You can see the previous example if you look at. You can see here only the hydrocarbons. Clear? So this is not the steric crowding here. So look at here. The first one has no resonance. So first one would be the better nucleophile. Now in the second and third, they both have resonance. You can see negative move here and this will give here. Clear? Now my question is, which one has better resonance? Like which one have stronger resonance? Second or third? Look at here the concept, very important concept. If you are going to draw the resonance structure of the third one, then it would be this. It donate, it breaks. Like that. So they have identical resonance structure, and negative charge is on oxygen in both the structure. So this is the most stable form. This is the stable one. But if you look at this iron phenoxide and this is called as, and if you are going to draw the resonance structure, So you can see here negative on carbon, here negative on oxygen. And this is not identical, no identical. Whenever there is a comparison between identical and non-identical resonance structure, identical always dominates. Identical always dominates. So identical have good resonance. It means whenever resonance is high, nucleophilicity decreases. And this one is a weak resonance if you compare with the third. So this one is a good nucleophile. So first, second, and then third. It makes sense. The reason is that third have identical resonance structure. Identical means they have equal stability, but second have non-identical resonance. So they have unequal stability in the resonance pairs. So that's why second is better than third, because second we have some tendency to donate its electron, because this is carbon negative, this is oxygen negative. So there is stability is not equal. If oxygen is not going to donate, it means carbon can donate. But here negative on oxygen in both the structure, which means it is not going to donate its negative charge to the any atom as a nucleophile. Please tell me it makes sense. My request to everyone, whenever there is an identical resonance structure, that would not be a good nucleophile. Okay? It is not. No. It is not related to benzene and other. Or whenever you have to compare the identical and non-identical, then identical would always be, you can say, more stable resonance structure. When there is a comparison of benzene containing system with a multiple compound, then you can say yes, this one is benzene which is aromatic, another one is not aromatic. Means you can compare this benzene related compound, then you can apply the same concept. But whenever there is a comparison between identical and non-identical, identical dominates in terms of stability of resonance. Resonance is, yes, of course, resonance high, nucleophilicity lower. Clear? Perfect. Now we have a term, nucleophilicity and basicity. In the next few sessions, you can see a single species can behave as a nucleophile and as a base. So we should know the difference of nucleophilicity and basicity. Do you know what is basicity and nucleophilicity? I have discussed what is nucleophilicity. Do you have any idea about the basicity? What is basicity? What is base basically? So basicity means tendency to donate lone pair of electron or electron to a proton. But nucleophilicity is a tendency to donate electron to any atom except proton. Okay. So if you are going to donate your lone pair of electron to a proton, that is considered as a base. And if you are going to donate its lone pair of electron to any atom like carbon or nitrogen or anyone, then it can be act as a nucleophile. For example, suppose we have NaOH, where you know that this should be negative charge, and here you have HCl. So now we're going to grab this H, so it would form H2O and NaCl. So this is OH and this is proton. So it can act as a base here. I am using the same species NaOH, but here we have CH3Cl suppose. Now this OH is going to attack over the carbon and Cl leave. So that would form CH3OH. So this time it is acting as a nucleophile. Do not think about the product writing here. Just look at the donating tendency. Here it can donate the electron to a proton, then act as a base, and this OH is going to attack on the carbon, so it can act as a nucleophile. Makes sense the basic difference? Yes, you can say, because nucleophile attack means nucleophile is a kinetic property. So it can move from one to another position. But base is not a kinetic. It can grab the proton. Yeah, that's the correct one. It can accept the proton. Yes. Easy. So basicity is basically related to a thermodynamic property. Whenever the term thermodynamic is used, that means it is related to stability. But nucleophilicity is a kinetic property, and kinetic means speed. Clear? So whenever you are moving in period on moving in period, nucleophilicity and basicity have same order. Same order. For example, CH3 minus, NH2, OH and F. So if you are going to arrange in the decreasing order of nucleophilicity, you can say this is related to the same period. So nucleophile order would be this. And the same order for the basic strength as well. Same order. Clear? Make sense? Because there is no much difference in the size once you are moving left to right. Size remains same. But in group, nucleophilicity and basicity have opposite relationship. Opposite relationship. So suppose we have fluorine, chlorine, bromine and iodine, and we have to arrange them in order of basicity and nucleophilicity. So nucleophilicity means iodine is better than Br, then Cl, then F. But basic strength is just opposite. Fluorine, then chlorine, then bromine, then iodine. Make sense? Please tell me everyone. Because of size, you know. So base can grab the proton. So bigger size is easy to grab a proton. But nucleophilicity is a kinetic property. It can move. So heavier size would be very like tough to move. That's why we can say smaller the size, better the speed and better the nucleophilicity. Okay. It makes sense. Okay. Now the next is nucleophilicity in solvent. So, or you can say effect of solvent in nucleophilicity. And you can apply the effect of solvent in group only, in group. And whenever in period, no effect of solvent. Okay, you have to follow the same order, means electronegativity order. Any doubt about this? Whenever you have a same group element and you are using the effect of solvent, then you can consider this. Clear? For example, suppose we have NaF, any ionic solid. Now you can break this into Na plus and F minus. So suppose you are using a polar protic solvent, polar protic. And we can consider H2O as a polar protic solvent. Now you know that you have two ion, Na plus and F minus. Suppose this is Na plus. So Na plus is get solvated by the oxygen of water. Because this is negative, this is positive, so there is an interaction. It should be dot, okay? Because it is a weak interaction. Do not make a solid line, it should be a dot. So now you can see this cation is solvated, means water molecule is going to surround this Na plus. So this is called solvation effect, which is known as solvated ion. Same you can do with the F minus. F minus is going to solvate with the hydrogen of water because hydrogen is positively charged if you're going to see the water molecule. Can you see this? So both is going to solvate it. Any doubt? Suppose this is NaF. Now I am going to use NaI. Now Na size is same. So the size of cation is not going to affect the nucleophilicity here. So you have to consider the anion size, F and iodine minus. So iodine minus have a bigger size. So whenever size is bigger, solvation is less. Solvation is less. Make sense? Please tell me everyone. If you have a smaller size, then high solvation. Solvation is high. The reason is that if you have a small ion, the water molecule can surround it, in all the sides, all the sides you can see. But it is bigger size, so we have very less solvation. You can see. It's a practical. If you have a small things around you, so you can just, cover it quite easily. But if you have a bigger one, then it cannot be covered easily. So same with the iodine and fluorine. Make sense? So if this F minus is going to be solvated by the water molecule with a larger in amount, then this F minus cannot act as a good nucleophile. It cannot attack to the any atom. Like suppose this is not going to attack over here because this is solvated. But this iodine minus here is less solvation, so it can attack, it can donate its electron to the R or any carbon atom or any of the group as a nucleophile. So it can donate as a nucleophile better because there is less solvation. Make sense? So whenever, look at the concept, whenever you have a polar protic solvent, whenever you have a polar protic solvent, size increases, nucleophilicity increases. Clear? Simple. So suppose I am saying we have to arrange this nucleophilicity order in methanol CH3OH, in methanol. So first of all, tell me what is the nature of methanol, polar protic or polar aprotic? Polar protic, good. So whenever you have a polar protic, what is the concept? Size increases, nucleophilicity increases or decreases? Tell me. Yes, whenever you are going to increase the size, nucleophilicity increases. So iodine, Br, Cl, F. Make sense? Any doubt? Clear? Now the next is polar aprotic. PAS in polar aprotic solvent. Polar aprotic we can consider, suppose acetone 1. So this is the negative, this is the positive, and suppose here you have NaF. So you know that suppose NaF dissociate Na plus plus F minus. So this is minus, so it would interact with this sodium plus. Okay, so O minus of the acetone molecule is going to solvate the Na plus. Make sense about it? Please tell me. So all the Na plus is going to solvated by the oxygen of acetone. Clear? But this anion, here you have a positive charge. Because of steric crowding around the carbon, you can see two bulky groups around the carbon. So this solvation is not good here. It means in polar aprotic solvent, anion is not solvated, is not going to solvate. No solvation of anion. No solvation of anion. Why? Because of steric crowding of polar aprotic solvent. Make sense? So we can apply here the charge. So fluorine minus, chlorine minus, Br minus, iodine minus. So this one have high electron density. Why? Because of smaller size, have negative charge. This one is a bigger size, chlorine, negative. This one is a more bigger, chlorine negative, and this is iodine. So electron density is high in the fluorine. So high electron density, it means it can donate easily. So we can say top to bottom, the trend should be like this: fluorine, then chlorine, then bromine, then iodine. This would be the correct order. So basically, whenever polar protic solvent, you can say size increases, nucleophilicity increases. But in polar aprotic solvent, size increases, nucleophilicity decreases. Clear? Make sense? Any doubt? Please tell me, everyone. My question to everyone. It makes sense? Okay, let me give you a question. Give me 1 second. What should be the order? Nucleophilicity. What is the nature of DMSO? Very good. Now, second thing. They are related to same group or same period. Whenever period, no need to apply solvation effect or solvent effect. It would always be considered in a group. Yes, group. So DMSO is a polar aprotic. So size increases, nucleophilicity. Yes, decreases. So H2O would be a better nucleophile. Make sense? Please tell me it makes sense. Okay. Now another question. If the nature of solvent is not given, then always consider as a polar protic solvent. So I'm not going to give you here the nature of solvent. So it means it is a polar protic solvent. Clear? What is the nucleophilicity order here? Tell me. Whenever you have something like that, always identify the donor atom very first. So here we have two kind of donor atom, oxygen and sulfur. Oxygen and sulfur. Now tell me, what is the position of oxygen and sulfur? Is it the same group or same period? Same group. Good job. Same group. Same group. Yes. So whenever is in the same group, what should be the order? Oxygen is a better nucleophile or sulfur? We don't have the nature of solvent. Remove the solvent condition. Oxygen or sulfur? Sulfur. Please review. Okay. Bigger the size, better the nucleophile. Okay. So sulfur is a better nucleophile. So the fifth would be the best. Now the next, we have this, and this. Now let me know which one would be a good nucleophile after that. Now next is wait, do not jump to any direct one. Look at here. Negative charge is better than lone pair. Negative charge is better than lone pair. So first is negative, third is negative, fourth is negative, but second is a lone pair. Make sense? Wait. This is OH minus I wrote here. OH minus. One thing I can say, second would be the last. Why? Because this is lone pair one. Clear? Now we have this oxygen this is, you can see the CH3OH having a lone pair. Negative is a good nucleophile than lone pair. Now the first, third, fourth, they are all negative. Same donor atom. Now effect of resonance. Okay, between first, third and fourth, which one has no resonance? Which one has no resonance? Third. So third. Now between 1 and 4th, we have done this already. It would form identical. And this is non-identical. So first and then 4th. Make sense? Please tell me everyone, it makes sense? All done? Okay. So in the next session, I will discuss to answer these type of question. Is it better to go off size and then resonance? Wait. It depends on the donor atom the very first. If you have a different donor atom, then go with the size. Okay. But always apply electronegativity as well. Like suppose we have CH3OH and supposed to be CH3SH. So you can see oxygen and sulfur belongs to same group. So this one would be a good nucleophile. Okay. If you have another species, suppose nitrogen containing, suppose I am saying we have NH2, H2S, and H2O. So now look at the position of these atoms in the periodic table. So you know that the elements are arranged in this way. Here sulfur, here phosphorus. So now look at here, nitrogen, oxygen, sulfur. Now you know that if you are moving left to right, electronegativity increases, nucleophilicity decreases. So oxygen and sulfur is right to the nitrogen. So it means nitrogen is a better nucleophile. So first would be nitrogen. Now oxygen and sulfur, both same group. So size here. So we can say third, then first, second. Make sense? Okay. So in the next session, we will discuss leaving group, then potential energy diagram, reaction coordinate, which is called as, suppose you have something like this, then you should know what is my intermediate, what is transition state, or what is slow and fast step, like that, which one is a rate determining step. So we will discuss this kind of graph, and then we will discuss stability and rearrangement of carbocation. Rearrangement of carbocation. Listen me, this is very systematic way to learn reaction mechanism, because this and this one is going to apply in SN1, SN2, E1 and E2. If you are not good in nucleophile basicity, weak and strong nucleophile, then you cannot answer SN1, SN2. So we are going to move slowly, but we will cover everything. We are not going to miss anything before SN1, SN2. And now I would be more regular with my group sessions. So the next session on Saturday, let me know which one would be good, Saturday or Sunday. And my plan in the daytime, maybe 11 or 12. Please tell me everyone. 11 a.m., 12 p.m. or 12:30. This time I can do. Yeah, this week. This week. You can celebrate Father's Day in the night or evening. We can do the class in the morning, or at 11 a.m. or something. It would be just 1 hour session, okay? So my plan is like 2 to 3 times in a week now. Okay, I will try to do on Sunday, okay? And let's see. Yes, earlier, maybe 11 or 11, between 11 and 10. Oh, sorry, 11 and 12. Thank you so much, everyone. It makes sense, the session. Please review everything before the next class. This is my request to everyone, please. It could be good if you can post something about me on my group. Bye bye. Good night, everyone.